right, welcome back, everybody. We're back here in the swelter shelter at the end of our heat wave. This is supposed to be the last day, and I'm going to keep the door open so that I don't start sweating as much as I did the last time I made one of these videos. We'll see how it goes. A little bit earlier in the morning, too, so hopefully it'll be just fine, but we'll find out. The one positive is that, having said that, I'm not going to talk more about the weather much for the rest of this lecture. Instead, I'm going to talk about normal distributions and something called Z-scores, or if you prefer, if you're more Canadian than me, you can say Z-scores. And in fact, it is Canada Day, the day on which I'm actually recording this. I will say Z-scores once, but that's it. So what does that mean? What are we getting into? So let's start out where we were at the end of our last lecture. I guess I'll also mention that I'm borrowing a lot of these slides from that Introduction to the Practice of Statistics textbook. So they might look a little bit different and they're presented a little bit differently as well, but they're convenient because they get the message across in a slightly different way. And the first point they get across is this idea of linear transformations that we talked about last time. So on this slide, it's described as variables can be recorded in different units of measurement. And the example they use is the same one that I used, which is converting between Fahrenheit or Celsius. There's, a certain amount of heat out in the world right now. You can measure it in Fahrenheit. You can measure it in Celsius. There's a way to go back and forth between the two, but there's sort of just one thing that we're measuring, really. The way we do this in this particular case is that we're talking about a linear transformation. In here, they write the equation for a line in yet a third way. Compared to the two ways I wrote it in the previous set of slides. So they talk about x sub nu, whatever that might be, equals a plus bx. I would prefer to think about this variable as y rather than x sub nu. But be that as it may, in this case, the a represents the intercept of the line and the b represents the slope. And this is actually kind of a more expandable way to write this equation because you might have like an x squared term here and you could just say plus cx squared, and that would be a nonlinear transformation to be quadratic or whatever it is. And then you can keep just going from there. We're going to set that aside though, just to acknowledge that this is sort of a more rational way to write the equation. And then the way it corresponds to this conversion, equation or algorithm we use to go back and forth between Celsius and Fahrenheit is that A, the intercept is 32, and B, the slope is 9/5, so they give you in very small font that equation down here. So we've seen all this before, and we've also seen this information before as well, such that linear transformations don't change the basic shape of a distribution, like their skew or symmetry or whether they're multimodal or what have you, but they do change the measures of center and spread according to specific parameters. So multiplying each observation by a positive number b multiplies both measures of center and spread by b. So by measures of central tendency, we mean like mean and the median, and spread, things like the interquartile range or the standard deviation, so on and so forth. Those get expanded by b, or if it's b is small, you also can compress them. But a, the intercept, is only going to have an effect on the measure of central tendency. So if a, whether it's positive or negative, will be added to the measures of central tendency and to the quartiles, but it won't change the measures of spread. So we've seen that before, but kind of the interesting fact that we want to focus on in this lecture is we're going to use these linear transformations to change the way we represent certain distributions, but we can be comfortable knowing that we're not going to change the basic shape of the distribution when we do that. Give me a second. Which is principle number 1 here of linear transformations. So in particular, we're going to think about that sort of conversion a lot with respect to normal distributions, which we saw early in the semester for the class. So before I get into that, I need to introduce this concept of a density curve, which is similar but not exactly the same thing as what we've been looking at up till now when we look at distributions. So normally when we look at distributions, there's a couple of examples here of vocabulary. Like, it doesn't really matter what this is, but they're representing vocabulary scores for, I guess, students in particular. Grades, or I guess, no, if say maybe this is a group of students that is in maybe 7th grade or grade 7 if you're a Canadian. And so they're looking at their vocabulary score, and some students in grade 7 have a lower grade vocabulary score, and some students have a higher grade vocabulary score, but they're basically centered around 7, more or less here, right? And in fact, we see, so like the way we normally plot this distribution or histogram is by counting the number of students who have these specific scores in these specific bins. Like maybe this is from 6 to 6.5 or something like that, and this is 6.5 to 7, so on and so forth. And so maybe this bar, this column has like 25 students in it, and this one has 26 or something like that. So that's actually representing specific data that we've collected. And then we see when we plot it out that it has this sort of nice bell curve shape to it, but it's not exact, right? It's still got, quantal leaps from one bar to another because we're counting in specific numbers. What you can do, though, is you can sort of idealize that shape, right? So this red curve plotted on top of that histogram is an idealized view of what we kind of think that distribution is, or histogram is representing, which is called a density curve. And so this density curve we can define mathematically. We've seen the equation for normal distribution before, and we're going to see it again. But you could say just generate this curve based on the parameters of a normal distribution, and it's a pretty close match to the actual data we're seeing here in these columns or bars. So the crucial point here is that this red curve is not representing specific observations that we're getting from data we've collected in the world. It's a mathematical object, which is generated on the basis of an equation alone. So it's, for that reason, an idealization of what we're actually seeing out there in the world. But the nice part of this is that we can treat the density curve as a mathematical model and kind of pretend we see the underlying sort of population that generates this sort of normal looking histogram, even though it's not exactly normal. So when we have this curve, we treat it like a mathematical object. We can say we know exactly like, oh, there should be, if this is the actual sort of distribution underlyingly, if we were actually, well, I don't want to get into that, but say, let's just assume that if we were going to collect enough data from enough students over time that it would fall on exactly this sort of line, which again, we're just generating mathematically, then we could say, well, we know there should be this percentage of students, say with scores less than 6 on this grade equivalent vocabulary score. And we can calculate that percentage exactly knowing the mathematical properties of the density curve. So the total area under the curve, as it says here, is going to be equal to 1 if you want to think about it in terms of just a number. It might be easier to think about it in terms of percentages because we're going to divvy it up into different bits and pieces as we go through this. So the total area under the curve is equal to 100% just by definition. And that makes it easy to kind of make conversions between sort of different shapes of distributions or different kinds of density curves. They all have to have that property. So the area it also says the area under the curve for a range of values is the proportion of all observations for that range. Right. It's kind of, so I think the part of this graphic, which I'm maybe glossed over in not the most accurate terms, is showing you kind of that difference in terms of the histogram versus this density curve. So the orange bars here, they probably could have used a different color, but the orange bars here just show you the actual observations of scores on this test that are less than 6 for this group of students or whatever they are. And then compare that to this orange area under the curve here, which closely aligns with the bars, but not exactly aligns with the bars, right? So there's a little a few bars here which go above the red line. There's a few that go underneath it. So the shaded area here just represents the scores for this density curve, which should be under 6. And we should be able to calculate, we can calculate exactly what percentage of the area underneath the curve will be less than 6, knowing the exact mathematical properties of this density curve. Okay, hopefully I didn't garble that too much, but that's the general idea, is that we're going from specific observations to something sort of idealized and abstract. If you're a linguist, this is a little bit like going from the phonetics world to the phonology world. We're getting sort of these idealized contrasts as opposed to, oh, we're messing around with like sounds and people's tongues and stuff like that. Okay, so, right. Density curves, this says they come in any imaginable shape, and it gives you 4 different density curves you can play around with. We've kind of talked about some of these when we went through the different sort of distribution shapes at the beginning of the class. It also says some are well known mathematically and others aren't, and by that, basically they could say, we can come up with an equation for generating some of these curves, and for others it may be more difficult to do that, or we don't know how to yet. But the one point I want to make here is it says density curves come in any imaginable shape. What you won't see with the density curves, well, at least it wouldn't really make sense, is if you had them sort of like having overhanging ledges or something, like if this one went up like this and then bowed out over here and then came back over here. That's not going to work. They all kind of have to have a meaningful positive value for this variable as it goes along this x-axis in some way. So in kind of an extreme case, you can get this sort of like square-like distribution going from like 0 to 1 or whatever right from the start. But it's still not going to have like an overhanging ledge because that wouldn't make any sense. So it kind of has to be continuous in that way. Otherwise, like it says, they can come in any shape, and then you just have to work out the math for describing them if you want to play around with them in the way that we're going to play around with these curves as we go through this lecture. This talks about median and mean. We've talked about this as well. It gives a couple of kind of interesting definitions of how those two concepts differ in terms of density curves as opposed to like samples of distributions. It says the median of a density curve is the equal areas point, the point that divides the area under the curve in half. So in this sort of normal distribution case, the median and mean are the same, so we're going to get kind of the exact same halves for whatever definition we use. But over here we have the median here, and the idea is that this is supposed to be half the area, including this little bit here, and it will be equal to the area under the curve over on this side. The mean of the density, on the other hand, is the balance point at which the curve would balance if it were made of solid material, which shoves the mean over in this direction a little bit, because I guess there's more weight in this part of the distribution, or is as much weight in this half of the distribution as there is here, but you wouldn't get that balance point if you didn't include this little slice on this side of the mean, as opposed to what you do with the median where it's on the right-hand side. And so we don't need to worry about this so much. We've talked about this before, and we know how to calculate both the mean and the median. This is just sort of a graphical representation of this. And the other point that we've made before, or hopefully I've made before, is that when you have this sort of skew to the distribution over here to the right, that's going to normally pull the mean over to that skew more so than it does the median, which is the point that is made down here at the bottom. Okay, I'm not going to say anything more about that. I do want to get into these normal distributions, though, or Gaussian distributions, if you'd rather think about Carl Gauss. So this is this family of symmetrical so-called bell-shaped density curves defined by these two parameters, one of which is the mean and the other which is the standard deviation. So here's this equation, which we've seen before. We didn't look at the specifics very much. It's got a couple of constants in here, which you might recall from high school math class or wherever. Like pi is a commonly known one, and it's described down here. So it's whatever the diameter of a circle divided by the radius. Then it's e, which it calls the base of the natural logarithm, and it gives you the actual specific numbers for both of these constants. So these are not variables; they're constants. They're like numbers that take the form of letters when we write them out. The part of this that's interesting for us to think about, based on what we know now, are these other parameters, sigma and mu. So I've presented both mean and standard deviation to you guys using different representations up until now. So when we normally talk about the mean of a sample, we represent it with like x bar, the little line over the top. And here they're representing it with a mu, the Greek letter mu, which is the sound in ancient Greek. And then standard deviation is no longer s, it's sigma, which is the S sound in ancient Greek or even modern Greek as well. So it's this little kind of cannonball looking thing. That's the letter sigma in Greek. And that's standard deviation here. So the question is, why are we using Greek letters as opposed to sort of normal variable notation, like just Roman letters, Roman alphabet letters, like X and S? We're using mu and sigma. And the idea is we're going into sort of like the idealized world by using these Greek letters. So that's what it represents, is that we're now dealing with an idealized mathematical object for which we can know the exact mean and the exact standard deviation without, having to go through this process of sampling some data and taking basically a guess based on just a small slice of a larger distribution. Yeah, I mean, I kind of can think jokingly in my head about how we're getting into the Platonic world here. This is where phonology exists. This is where Plato's pure forms exist. And maybe that's why we're using these Greek letters. If it helps you to think about it that way, go ahead. It does for me. But the main thing is that it's representing something different. So the Greek letters are representing properties of a mathematical object. The Roman letters we'd use, like X and S for a distribution, represent properties of some sampled data that we've collected in the world, rather than just math. Okay, I'm not going to say anything further about that. I will walk you through this slide, though, which hopefully encapsulates some information that is now a little bit familiar. So let's say we have a family of density curves or normal distributions where the means are the same, but the standard deviations are different. So these are all centered around the number 15, or mu equals 15. But if you have less standard deviation, you get this blue one in the middle here. Well, they're all in the middle, but this one stands out more because it's leptokurtic, right? So the mesokurtic one is the green one, which has a standard deviation of 4, and then this flat one, the platykurtic one, has a standard deviation of 6. But they all have the same mean. They're just either thinner or fatter, basically. Based on standard deviation. If they all have the same standard deviation but different means, you get this sort of picture where the one with a lower mean is down here, the blue, which is supposed to be centered around 10. Maybe it is. And this one is centered around 15. This one's centered around 20, so on and so forth. Hopefully this is all old news to you guys now, but in case it's not, there you have it. What should be new news is actually something useful, which you will probably remember, or hopefully will remember even after this class is done. And this is what's called the 68, 95, 99.7% rule for normal distributions. So yeah, going back here, just think in terms of standard deviations a little bit for these normal distributions. The way it works out, because these are mathematically defined and we can calculate these numbers exactly, if you take the slice of a normal distribution that is within one standard deviation of the mean, then you get basically 68% of the area underneath the whole normal distribution curve. So 68% of this density curve fits into this pale slice here in the middle. Yeah, that's within one standard deviation of the mean. This graph also makes a nice little point, which is useful because I don't really have drawing ability at the moment, but that sort of one standard deviation from the mean is at this inflection point, so-called, where the whole curve kind of goes from being pointing downwards to sort of collecting upwards, if you want to think about it that way. And the curve itself kind of makes that switch where you get the one standard deviation marker. So you can kind of keep that in mind just as a graphical reference point for how to interpret these normal distributions. We can continue on with this sort of analysis and say that about 95% of the observations are within 2 standard deviations of the mean. So that's extending out over here. And there's not as nice of a defining point here on the curve for that point in terms of standard deviations. But what we're doing, or what we're saying here, is basically that 95% of the whole area underneath the curve fits into this width here, leaving just these bits on the side outside of that. But if we continue on and expand out to 3 standard deviations, we can expect to find 99.7% of the data within 3 standard deviations of the mean. Yeah, so this gives you an example of a height distribution, and in particular women's height, which is centered around 64.5 inches. Can't off the top of my head make the conversion for that with centimeters, but I'll say that if you are familiar with this way of measuring people's height, 64.5 inches is 5'4.5". That's the average height for women, and that can vary a bit from country to country or culture to culture, whatever. But we'll just roll with it here. It's the data they have. It turns out the conversion for going from inches to centimeters, if you're not used to thinking in terms of feet and inches, is pretty simple. There's 2.54 centimeters in an inch. So if we just use R as a calculator, we can say the average height for women is about 164 centimeters, 1 meter, 64 centimeters. So maybe that makes it feel more familiar to you. I don't know. This is another funny thing about Canadians speaking on Canada Day, is that somehow they don't like talking in terms of Fahrenheit, but they're totally okay somehow with talking in terms of feet and inches, especially when it comes to height. And then there are also Canadians who are okay with using the metric for height. So whatever, you got both now. But the average is about 5'4.5", it turns out. And then the standard deviation is 2.5 inches. So that means we'd expect to get 68% of women having a height between 62 inches and 67 inches. So just 64.5 is the mean. Add 2.5 to that, you get 67. Take 2.5 away from that, you get 62. So 68%, 2/3 of women, more or less, have a height between 5'2" and 5'7", which I think probably matches up pretty well with our experience. But we'll double check here in just a minute. I'm not going to say more about that note at the bottom because I've already talked about it. But I do want to kind of jog your memory or give you a pop quiz here, just to make sure that you understand what this means. So if I say 68% of the observations in a normal distribution are within 1 standard deviation of the mean, how many observations are below 1 standard deviation above the mean? And to put that in sort of non-text terms, but in graphical terms, what I'm asking is, at this point, which is 1 standard deviation above the mean for this particular distribution, how much of the distribution is below 1 standard deviation above the mean? How much can I fit not just into the slice in the middle, but also including this tail over here on the left-hand side? How can we figure that out? I'll give you a second to think about it. And usually we work through this together in class on the board. I'm going to have to talk my way through it here, but hopefully it'll still make sense in the end. So let's say if 68% of the observations are within 1 standard deviation of the mean in that middle slice, then that means that 32% of the observations are not within 1 standard deviation of the mean. So I'm going to go back to the graphic again and basically say, remember, we said this is a density curve and it's defined in terms of having 100% of the whole distribution under this curve. So if we just have 68% here in the middle, then there's still 32% left over, right? So 100 minus 68 is 32. And that 32% has to go in these sort of tails on the periphery of this distribution. And that also tells you something else, because we know that a normal distribution is symmetric, right? So that means that 32% is going to be evenly split on either side of the distribution. And knowing that, going back here again, I've got 32% out of these two tails, and they're equal to each other. So that means that 32 divided by 2 is in each part, each half on either side. So that means I've got 16% over here, and I've got 16% over here. And what I want to find out is how much do I have in this whole part of the distribution here, excluding what's above 1 standard deviation above the mean. I know I've got 16% on either side. So if I follow this slide through to its conclusion, that means I've got 84% of the distribution below that 1 standard deviation line, and 16% of it is going to be above that 1 standard deviation line. So there's a couple different ways you can think about it. I'm saying I've got 16% here, and then that means the rest of the 100% has to be over on this side, which is 84%. And the other way you can think about it is say, well, I have 68% here in the middle, and I know I've got 16% here on this side. So 68 plus 16 is 84. But you get to the same point either way you take it. And hopefully that makes sense as well. Basically, 84% of women will be 5'7" or less in terms of their height, or whatever I said. I didn't actually calculate what that would be, but we can do that really quickly. 84% of women will be 170 centimeters or shorter, basically. Yeah, you can go take a poll if you want to find out if it's true. In the meantime, I'm going to give you a moral of that story. The moral of the story is something I've told you already, which is the basic principle of using density curves. They're mathematically defined. So knowing the exact properties of that curve, the exact mathematical properties of that curve, we can easily go back and forth between standard deviations from the mean and proportions of the distribution above and below the mean. So to, again, go back to the graphic, I can think of this point here, this 67 inches point, as being one standard deviation above the mean. And I can convert, knowing where I am in the distribution in terms of that standard deviation, I can say, well, I've got 84% of the curve to the left of that point, and I've got 16% of the curve to the right of that point. Just knowing the standard deviations gives me that information about the proportions of the curve. And I can go back and forth as well the other way, say, well, I know I'm at a point where I've got, 84% of the distribution to the left of this point and 16% of the distribution to the right. What does that mean in terms of standard deviations? It means I'm one standard deviation above the mean. Okay, I'm rattling along here, but this is kind of the crucial point of this lecture, is that we want to sort of live in a world where we can just kind of deal with the data in these more abstract terms, in terms of standard deviations, without thinking about kind of uglier nuts and bolts like specifics in inches or centimeters or whatever, right? Like there's different ways to measure the height of something, just like there's different ways to measure the temperature outside. And yeah, you could say, well, why don't we just force the whole world to go metric? But I'm American. I can assure you the US isn't going to change anytime soon. So we can just ignore all that and say we're not going to deal with things in terms of inches or centimeters. We're just going to deal with things in terms of their standard deviations. And we're going to make that conversion, and then you can further convert from there to like whatever specific measurement system you want to use. But we're going to make that conversion by doing what is called standardizing the normal distribution, which is a really funny way to say it, because we're going from something that's normal to something that's standard normal. So a standard normal distribution is always going to have these properties. Its mean is always going to be 0, and its standard deviation is always going to be 1. And this, in my experience, it's a bit tricky to remember the terminology, because if you're like me, you think that something that is normal is also something that is standard. Yeah, maybe, but not in this context. So a normal distribution is just a distribution that follows that curve according to the math that Carl Gauss came up with. But a standard normal distribution is a distribution which has that curve shape, but on top of that, it has these specific properties. The mean is 0, and the standard deviation is 1. Yeah, so try to keep that in mind, but please don't call it a standard distribution, which is a mistake that's easy to make and that I myself have made before in my life. We'll just call it a standard normal distribution, and we're going to convert any normal curve with mean of mu and a standard deviation of sigma into one that now has a mean of 0 and a standard deviation of 1. So we'll do this for our height curve first, and the important point here is that the shape of the distribution is going to stay the same, because the way we're going to make this conversion is through a linear transformation, conveniently enough. So this is going to look exactly the same. And we're also going to have the same sort of properties in terms of like how much data fits within various slices of the distribution. But we're going to kind of make that part of it explicit by no longer having to think in terms of, whatever arbitrary specifics like height or temperature or whatever are on this x-axis. And instead, we're just going to plot the standard deviations on the x-axis. And in fact, these are now being labeled here as z, as you might see, or Z, I guess. I'll say it again. Great job, Canada. Anyways, these are going to be called Z-scores. And for each x, as it points out here, we have to calculate a new value called a z-score, called a z-score, and we'll just plot that on the x-axis. And these are basically going to be the number of standard deviations that point is away from this mean of 0. So we've got positive z-scores on this side, and we've got negative z-scores on the left-hand side. Okay, what does that mean exactly? I'm getting a little bit ahead of myself, but like I said, we're going to basically apply a linear transformation to this to get this to work. And it may not look exactly like a linear transformation when we look at this equation right off the bat, but it is. We're basically taking our observations x, we're applying this transformation to it, which is not super complicated, but we'll walk through the details, and we're going to get this new variable called z. Before we had y on this side of this equation, but z is good enough. And then what we're doing here is just two operations. Unfortunately, they're different from what we saw before because they're kind of like the counterpart operations. So instead of adding, we're going to be subtracting, and instead of multiplying, we're going to be dividing. But we wind up in the same place. Like I said, it works for both kinds of operations. But basically, what we get out of a z-score is that we're measuring the number of standard deviations that a data value x is from the mean mu. And we saw that before on this previous slide. So instead of thinking in terms of like 67 inches, I'm just going to say, well, I'm one standard deviation above the mean. And since I'm thinking in terms of standard deviations, I'm no longer plotting x values. I'm plotting these z values. The specific equation to do that is that z is equal to x minus the mean, all that divided by the standard deviation. Okay, so that's pretty straightforward. And there's a few examples here, and I think, let's see if I can edit this on the fly. I cannot edit that on the fly. The examples that this gives you are maybe, no, I'm not going to be able to do this. So there's examples that give you, say, let's say you're one standard deviation above the mean. Then we'd expect z to be equal to 1. The way it works out in this equation is that in that case, x equals mu plus sigma. That makes you one standard deviation above the mean. So if you plot mu plus sigma in this equation here, you get mu plus sigma minus mu up here on the top half of the equation. The mu's will cancel each other out. We'll just get sigma over sigma, which is 1. Likewise, if you're 2 standard deviations above the mean, then z equals 2. So in this case, you get mu plus 2 sigma. And then if you substitute all that for x in this equation, you get mu plus 2 sigma minus mu over sigma. The mu's cancel each other out again. You get 2 sigma over sigma, which equals 2 again, which is where we want to be, right? That's how you calculate z-scores sort of in the abstract. We'll see a few examples coming up, and I'm also going to make a sort of separate lecture for that altogether because this is an important concept to know. But basically, overall, one thing to keep in mind is that when x is larger than the mean, like if you're a woman with a height of greater than 64.5 inches, your z-score is going to be positive. If x is smaller than the mean, if you're a woman with less than that height, then you're going to be in the negative territory for z-scores. That's just a really nice way to sort of divide up the whole spectrum of what you're getting in the distribution because the whole thing's centered around 0, but above average is positive, below average is negative. All right, so this is the distribution we've seen before many times. Right, so, and this is also asking a question that I've already answered, but so women's heights have a mean of 64.5 inches and 2.5 inches is the standard deviation. What percent of women are shorter than 67 inches tall, which is 5'7"? And yeah, I'll just take another drink here and you can think about how we already answered this question. But if we're at 67 inches in height for women, then we're one standard deviation above the mean, and we're asking what's in this light shaded area here. We know that that is going to be 84%, and this walks you through the math. So 67, you can calculate first the z-score for 67. You just plot that value into the x here in the equation. So 67 minus 64.5 equals 2.5, and the standard deviation is 2.5, so 2.5 divided by 2.5 is 1. That puts you 1 standard deviation above the mean. And then we already know that if we're at that point in the normal distribution, then we're going to get 84% of the distribution to that left-hand side. That means that 16% of women will have a height that's higher than 5'7" or 67 inches. Yeah, so I'm not going to say anything more about that. I might give you another example, though, because we've already kind of done this one. And I'm going to do this on the fly because I'm dumb and did not prepare it. I just want to do it spontaneously here. But let's go back to this. Let's say we have a woman with a height of 69.5 inches. So we're right there. So what does that mean? How many women have a height less than 69.5 inches? So this is 5'9.5", which is fairly tall for a woman. And we can kind of get a better sense of like how fairly tall it is by knowing like what is the percentage of women who have that height or more, which is kind of the same thing as asking what's the height of percentage of women who have that height or less. So with 69.5%, 69.5 inches, one thing to note here is this rule we've been using. So we said there's 95% of a normal distribution is within 2 standard deviations, right? I wanted to kind of walk this out, but I don't think I'm going to be able to. So if 95% of a distribution is within 2 standard deviations, that means there's only 5% left that's on either side of that 2 standard deviations from the mean, right? So that means there's 2.5% here, and there's 2.5% over here as well. And that means that at this point, I've got 95% here in the middle. I've got 2.5% over here as well. That means that I've got 97.5% of the distribution to the left of this 2 standard deviations point. There are 97.5% of women who are 69.5 inches or shorter, basically. But what you need to do at this point is to stop thinking in terms of these inches and just think about it in terms of the standard deviations. Because this is going to apply not only to like women's height, it's going to apply to things like temperatures or anything else that's normally distributed. IQ is another one that just pops into my head. Okay, so we talked about this. I gave you an example I talked through. Should have shown it to you, but hopefully you still remember. I want to show you something else, which you're not going to need to remember, but I'm just going to do this because I'm an old man. And when I took stats for the first time, it was at the end of the 90s when I was a grad student in linguistics. And when we did it back then, we had to, we didn't have R that could do all sorts of amazing math for us. We didn't have any software at all. In fact, we just learned from a book and just thought about it sort of theoretically. And then if we wanted to find out sort of, what these conversions were between z-scores and proportions, we had to go to a table in the back of the book and just sort it out by sort of thumbing our way through these numbers. So I'm just kind of pointing this out on the one hand to say, well, you're lucky, kids. You don't have to spend your time doing this. You have all sorts of amazing software that can do it for you. And then also, because the software can do it for you, that means you're expected to do hard work in some other fashion. But the other part of that is that stats changes in a hurry. So I'm trying to teach you how to do stats to the best of my ability at this point in time in 2021. But I took stats in, I think, 1998, 23 years ago. So if you're going on through a career in stats, you're going to have to figure out a way to keep up because things are going to just keep getting better. But back in the bad old days, the way you would have to do this is say, well, let's say we have a z-score of negative 2.4. And then you look through this table and you find negative 2.4. And then this table tells you the percentage of the distribution that's to the left of negative 2.4, which is 0.0082 of the distribution, which is 0.82%. If you had negative 2.41 for your z-score, then it's 0.008 of the distribution is to the left, so on and so forth. So you're moving further and further away from the mean. You get smaller and smaller proportions as you go. Yeah, again, we don't have to do this anymore, so I'm not going to belabor this point. But like this shows you, say, there's 84% of the distribution to the left of 1 standard deviation, and then it just kind of keeps going up from there, so on and so forth. Yeah, so I'm not going to say anything further about that, but I do want to tell you how to do this in the modern world. So in R, you can convert between z-scores and proportions of a standard normal distribution with two commands. And the first one will convert a z-score into a proportion, and it's called p-norm. And I'm going to jump out of this slide here for a second to show you this in operation here in R. So p-norm 1 gives you 0.8413, so on and so forth, of the distribution. That's the percentage of the distribution that's to the left of the z-score of 1. And just a second ago, we were calculating the same sort of value for z-score of 2, and we came up with something like 97.5. I'll show you how to do that. P-norm of 2 will give you something close to 97.5. It's 0.9772499, so on and so forth. But this is taking a z-score and telling you what proportion of the distribution is to the left of that z-score. What proportion of a standard normal distribution is to the left of that z-score. There's also an operation, a command you can use to go in the other direction. It's called qnorm, and that will convert a proportion into a z-score. These are both useful depending on what context you need to use them in. So I will show you, we'll take this value, which is supposed to be the percentage of the distribution to the left of one z-score. If I plot that into qnorm, I should get something close to 1. It turns out it's not exactly 1. This is supposed to be the z-score now for this proportion of the distribution. It's almost 1. It turns out it's not exactly 1 because R has to do some rounding off sort of behind the scenes just to make sure it doesn't have to store like millions and millions of digits for every single variable that it has to be concerned with. So it's not quite exact there. If you want to get the exact sort of right answer, you can do this sort of nesting thing. Say, instead of copying all these numbers by hand, I can just take the output of this command here and plop it into the parentheses for qnorm. And I should, when I do that, get a value of 1, and I do, and that's kind of not really that exciting, but it's just showing you that R has some rounding off things, which you can kind of avoid by sort of saving yourself some trouble as well, and just sort of using the outputs of these formulae when you're using them for other formulae as well. You're not ever going to have to do this sort of thing other than just as a demo to show people how things work conceptually. But just so you know, if it looks like something should be exactly 1 or some value and it's not, it's because of just technical details and how this is implemented. Not about you, but don't freak out basically if you see something like that. All right, so some finer points as well, give me a second, is that this, just so you know, this 68%, 95%, 99.7% rule, it's not exactly exact. I think when on the slide that first introduced those numbers, it said these are about the percentages on these sides of the standard deviations for these distributions. So here's the way it looks like in R. I'm kind of giving away the answer. Yeah, I'm giving away the answers too much here. So I won't. And you can just ignore what you just saw. But if I say, look at the percentage of the standard normal distribution within one standard deviation, the way I figure that out is to say I want to look at the percentage of the standard the percentage of the distribution to the left of a z-score of 1, and subtract from that the percentage of the distribution to the left of a z-score of -1. So I just get that slice in the middle without the sort of part on the left-hand side. I got to think about it in terms of your point of view. But slicing off both of those peripheral tails, what's left in the middle is about 68.26895%. Yada, yada, yada. So it's about 68%. If I do the same thing for 2 standard deviations, expand it out a little bit, but still cut off those tails, then I get about 95.4% of the distribution. So it's about 95%, but not exactly 95%. And this is the kind of question I was asking before, like what percentage of the distribution should be below 2 standard deviations approximately. We figured that out before. It should be about 97.5%. But when you plop that number into this qnorm command, 0.975, you get a value, a z-score value of 1.959964. So it's not exactly 2. It's also not exactly 1.96, but normally when you see people refer to this, you will see them sort of just use 1.96 and round this stuff off a little bit. So we're human beings, we're doing a little bit of rounding off errors here as well, I guess is the moral of that story. Also, to make these previous commands sort of explicit, I just want to show you. So pnorm2, that's the percentage of the distribution to the left of 2 standard deviations, and pnorm -2 is the percentage of the distribution to the left of -2 standard deviations. So this is about 97.7%. This is about 2.3%. If I subtract this from this, I'm going to get something close to 95%, but not exactly, right? So we're taking 97.7% of the distribution and subtracting 2.3% of the distribution from it, we get 95.4. That's how that works. Okay, just got a couple more slides here. Remember that since the normal distribution is symmetric, the proportions of the distribution in the right and left tails will always be equal to each other. So we just talked about pnorm of 2. And one thing that might not be immediately obvious is that if you say with pnorm 2, you're looking at the percentage of the distribution to the left of 2 standard deviations. And if I use this command, 1 minus pnorm of -2, this is going to show me what's to the right of -2 standard deviations in a standard normal distribution. Excuse me. So in case that's not clear, we'll crank through some of the math here. So again, pnorm 2, that's everything to the left of 2 standard deviations. Pnorm -2 is everything to the left of -2 standard deviations, but 1 minus pnorm of -2, remember the whole density curve, everything underneath it adds up to 1. So if I'm slicing off just the bit of the distribution to the left of -2 standard deviations, that leaves me with everything to the right of -2 standard deviations. So if I take the whole thing, which is 1, and slice off everything to the left of -2 standard deviations, it leaves me with everything to the right of -2 standard deviations. And that number is going to be exactly the same as what is in the distribution to the left of 2 standard deviations. Those two are equal to each other. So it's symmetric in that way. Everything to the left of 2 standard deviations above the mean is equal to everything to the right of -2 standard deviations below the mean. It works the same way. We've seen these commands enough, I think, at this point. But pnorm of -2, which is everything to the left of -2 standard deviations, is going to be equal to everything to the right of 2 standard deviations above the mean, which is about 2.3% of the distribution. And then also, I'll show that to you in R as well. If I'm adding up these 2 bits, right? So pnorm of 2, everything to the left of 2 standard deviations, and then pnorm of -2, everything to the left of -2 standard deviations. I add those together, I get 1. I get the whole thing. And I'll show you what this looks like graphically on the next slide, in case this is still confusing. Like I say, it's usually better to show than to tell. It's just hard to do it, both of those things, in PowerPoint. But we'll check out what that looks like on the next slide. In the next lecture as well, we'll look at some specific examples of z-scores from data that we've seen already in height and temperatures, just so you get more comfortable with what they kind of mean. So in this particular case, it's hard to see on this slide, so I'll read it to you. But this is a z-score of 2.33. And it's saying, well, that z-score is going to be way over here on the right-hand side of this distribution, leaving, and this is hard to see, an area of about 99% over on the left-hand side of this distribution, and about 1% over here to the right of 2.33. So maybe it can be a little bit easier to see over here. That is going to correspond to the same sort of breakup in the distribution we see, or split in the distribution we see when we go over to a z-score of -2.33. So that leaves only 1% of the distribution over here to the left of that, and 99% over here to the right of that z-score. let me verify that with just some R wizardry here. So if I have a p-norm of 2.33, again, this is giving me about 99% of the distribution, and a p-norm of negative 2.33 leaves me about 1% of the distribution, with, again, a little bit of rounding there to help us out. And then if I do this, it should wind up being the exact same thing as this. What that is saying, another way to put it is the way it's represented here at the bottom of this slide, is that if I add everything to the right of, I will fix this. I'll walk you through the example on the bottom of the slide first. Area to the right of Z is going to be, say, this. That is a way of measuring everything to the right of a particular Z-score. And that should be everything, should be 1 minus area to the left of Z. They basically balance each other out. And I've kind of garbled this a bit, so I'm going to stop before I make it any worse. But basically, this should equal 1. Because here we're looking at everything to the left of 2.33 and everything to the left of negative 2.33. But that is the same thing as, say, looking at this. So this is everything to the left of 2.33, and this is everything to the right of 2.33. We just kind of have to get there in a backwards way, but they wind up being equal to 1 anyways. I think I've said enough about Z-scores, at least in the abstract for now. Like I said, the next lecture will show you what they look like when you actually try to calculate them for real data. But hopefully you get the general idea. At this point, we're going to use these a lot moving forward, and they're also going to kind of lead us into how to do hypothesis testing using stats and sort of sampling from real observations and real data. So they're important, and if you don't understand them, you might want to go back and look through the basics of this lecture again, or hopefully get a better understanding when I talk about them in more nitty-gritty detail in the next presentation. So I'm going to stop now and just say stay cool. Happy Canada Day. See you soon.